Parallel universes, alternate realities, multiverses. These concepts have fascinated both scientists and science fiction enthusiasts for decades. The idea that there could be other universes, each with its own set of laws and histories, challenges our understanding of reality and the very nature of existence. Are we truly living in a single universe, or could there be countless other realities, each operating independently, yet somehow intertwined with our own? In this chapter, we will begin our exploration of parallel universes, starting with what they are, the theories that support their existence, and how this idea fits into the broader landscape of both science and philosophy. We'll also touch on how the concept of parallel universes has evolved over time, from early philosophical ideas to cutting-edge scientific theories in quantum mechanics and cosmology. What are parallel universes? At its most basic level, the idea of parallel universes suggests that there may be other universes besides our own, alternate realities that exist independently of our own universe, but are connected in ways that we may not fully understand. These universes may be similar to ours, or they may be vastly different, with different physical laws, constants, or histories. The term parallel universes is often used interchangeably with alternate realities or the multiverse. The multiverse theory proposes that the universe we experience is just one of many universes that could exist simultaneously. These universes could range from ones that are nearly identical to our own, with only slight differences, to ones that are completely alien, governed by entirely different laws of physics and structure. The idea of parallel universes has its roots in both philosophy and science. Philosophers have long speculated about the possibility of multiple realities, often framing the question in terms of modal logic, that is, the logic of possibility and necessity. In essence, if something is possible, then it could exist in a parallel universe. But it is in modern physics that the theory of parallel universes has gained the most attention, with some of the most important theories in quantum mechanics and cosmology suggesting that parallel universes may not just be possible, they may be a fundamental aspect of the universe itself. Theoretical foundations. From quantum mechanics to the multiverse. The concept of parallel universes first began to gain serious traction with the advent of quantum mechanics in the early 20th century. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales, the scale of atoms and subatomic particles. It is in this strange, counterintuitive realm that the idea of parallel universes begins to emerge. Quantum mechanics and the many worlds. Interpretation. One of the most prominent theories regarding parallel universes comes from quantum mechanics, particularly through the many worlds. Interpretation. The many worlds interpretation, proposed by physicist Hugh Everett III in 1957, suggests that every time a quantum decision is made, the universe splits into multiple branches, each corresponding to a different outcome. These branches represent different worlds or realities, where each possible outcome of a quantum event occurs in a separate universe. For example, imagine a quantum event where an electron can either spin up or spin down. According to the many worlds interpretation, instead of the electron simply choosing one state, the universe splits into two, one in which the electron is spinning up and another in which it is spinning down. In this view, every quantum event leads to a branching of the universe, creating an infinite number of parallel realities, each corresponding to a different possible outcome of every quantum decision. This interpretation challenges the traditional view of quantum mechanics, which suggests that quantum events have probabilities that collapse into one definite outcome when observed. The many worlds interpretation instead proposes that all outcomes are realized, each in its own branch of the universe. This creates a potentially infinite number of parallel universes, each slightly or vastly different from the others, depending on the choices made by particles and the interactions that occur. While the many worlds interpretation offers a compelling explanation for the existence of parallel universes, it remains a subject of debate among physicists. Critics argue that it is an extravagant solution that introduces a vast number of unobservable universes, and that simpler alternative interpretations, like the Copenhagen interpretation, may be sufficient to explain quantum phenomena. Nonetheless, the many worlds interpretation remains one of the leading theories in the search for a multiverse, offering a fascinating glimpse into the possibility of infinite parallel realities. String theory and the multiverse. Another major theory that suggests the existence of parallel universes is string theory. String theory is a theoretical framework in physics that attempts to reconcile general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which governs the smallest scales. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings that exist in higher dimensional space. String theory predicts the existence of multiple extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. In some versions of string theory, these extra dimensions could give rise to parallel universes. The concept of the multiverse in string theory suggests that there could be a vast number of universes, each with its own set of physical constants, laws of nature, and initial conditions. In the landscape multiverse model of string theory, the extra dimensions predicted by the theory allow for many different ways in which the fundamental laws of physics could manifest. Depending on how the extra dimensions are compactified or curled up, the resulting universe could have different physical properties. Some of these universes could be very similar to ours, while others might be completely different, with alternative constants of nature, varying laws of physics, and even different forms of matter. The landscape multiverse suggests that our universe is just one of many that exist in a much larger, higher dimensional space. These universes may be entirely disconnected from one another, with different physical laws governing each one. Some of these universes could even be completely incompatible with life as we know it, with different constants for gravity, electromagnetic forces, or the strength of nuclear forces. While string theory and the multiverse concept offer a potentially rich framework for the existence of parallel universes, they are still speculative and have not been confirmed by experimental data. String theory remains a work in progress, and many of its predictions are beyond our current ability to test. However, it remains a powerful and influential idea in modern theoretical physics, offering tantalizing possibilities for the existence of multiple universes. Cosmological models and the multiverse. Beyond quantum mechanics and string theory, there are other cosmological models that suggest the possibility of parallel universes. One such model is the inflationary multiverse. Inflationary theory, developed in the 1980s by physicist Alan Guth, posits that the early universe underwent an incredibly rapid period of expansion, or inflation, shortly after the Big Bang. During this period, the universe expanded exponentially, smoothing out irregularities and providing the conditions for the formation of galaxies and stars. The inflationary multiverse theory suggests that this inflationary process could occur not just once, but multiple times in different regions of space. Each region of space that undergoes inflation could form its own universe, with its own physical properties, laws, and constants. These universes would exist independently of one another, potentially with different initial conditions, and would not interact with each other. This idea has been proposed as a way to explain certain features of our universe, such as its fine-tuning, the apparent precision with which the laws of nature seem to be calibrated to allow for life. According to the inflationary multiverse theory, if there are an infinite number of universes, then it's not surprising that one of them, ours, has the right conditions for life. The idea of a multiverse would also offer a natural explanation for the apparent randomness and unpredictability in the universe, as different universes could have different physical laws, constants, and outcomes. Are we living in a parallel universe? The possibility that we could be living in a parallel universe is both exciting and unsettling. If the multiverse theory is correct, then our universe might be just one of countless others, each with its own version of reality. But how could we ever know if we are living in a parallel universe? After all, if these universes are completely separate, with no interaction between them, there would be no way for us to directly observe or detect other realities. Some physicists believe that we may be able to infer the existence of parallel universes through indirect evidence. For example, certain patterns in the cosmic microwave background radiation, which is the afterglow of the Big Bang, could provide clues about the structure of the multiverse. If the universe underwent a period of inflation, as suggested by inflationary theory, there may be subtle imprints of other universes in the cosmic background radiation that could be detected by future experiments. Another possibility is that the laws of physics in our universe might show signs of the influence of other universes. For example, if our universe is part of a larger multiverse, it could be possible that the physical constants that govern our universe, such as the strength of gravity or the mass of elementary particles, are influenced by the presence of other universes. If these constants are not fixed but vary across different universes, we might be able to detect their impact on our own universe. While these ideas remain speculative, they offer a tantalizing glimpse into the possibility that we might one day have evidence for the existence of parallel universes. Whether we will ever be able to directly observe or interact with these other realities remains to be seen, but the search for evidence of the multiverse is a driving force in modern cosmology. Conclusion. Are parallel universes real? The concept of parallel universes is one of the most exciting and perplexing ideas in modern physics. From the many worlds interpretation of quantum mechanics to the multiverse theories in cosmology, there is growing evidence that our universe may be just one of many, each with its own set of laws and physical constants. While we have yet to find definitive proof of parallel universes, the theoretical models continue to evolve and provide fascinating insights into the nature of reality. Whether we will ever be able to prove the existence of parallel universes is still uncertain. But the search for answers to these profound questions pushes the boundaries of human knowledge, forcing us to rethink our understanding of the universe and our place within it. If parallel universes do exist, they may not only reshape our understanding of the cosmos, but also offer new possibilities for exploration, discovery, and understanding. For now, the concept of parallel universes remains one of the most exciting frontiers in physics, a mystery that continues to inspire our imagination and our quest for knowledge. And whether or not we find definitive proof of their existence, the pursuit of this knowledge will undoubtedly lead to new discoveries that will deepen our understanding of the universe itself. The idea of parallel universes becomes even more fascinating when we dive into the realm of quantum mechanics, where the nature of reality becomes increasingly strange and counterintuitive. At the heart of quantum mechanics lies the many worlds interpretation, MWI, one of the most radical and intriguing ideas in physics. This interpretation suggests that every time a quantum event occurs, the universe splits into multiple branches, with each possible outcome of the event being realized in a separate universe. In other words, every possibility, no matter how improbable, happens, but in a different version of reality. This leads us to the question, could there be an infinite number of universes, each representing a different version of reality where different outcomes unfold? In this chapter, we will explore the many worlds interpretation of quantum mechanics, examining its origins, the scientific theories behind it, and how it fits into the broader context of parallel universes. We will also discuss the implications of the many worlds hypothesis for our understanding of reality, determinism, and free will. Quantum mechanics and the observer effect. To understand the many worlds interpretation, we must first look at the foundations of quantum mechanics. Quantum mechanics is the branch of physics that describes the behavior of particles at the smallest scales, atoms, electrons, and photons. Unlike classical physics, which treats objects as having definite properties, quantum mechanics introduces a level of uncertainty and probability. At the quantum level, particles do not have a specific position or velocity until they are observed or measured. Instead, they exist in a superposition of all possible states, with the probabilities of these states determined by wave functions. The observer effect is a key concept in quantum mechanics. It suggests that the act of observing or measuring a quantum system causes the wave function to collapse, and the system takes on a definite state. For example, when an electron is observed, it appears to be in one position or another. But before being measured, The electron exists in a superposition. It is, in a sense, in all possible positions at once. The act of measurement forces the electron to choose one of these positions. This is known as wave function collapse. However, the process of wave function collapse has puzzled physicists for years. If particles can exist in multiple states simultaneously, then why does the universe choose one outcome when we observe it? What happens to the other possibilities that were not observed? This is where the many worlds interpretation steps in. The origins of the many worlds interpretation. The many worlds interpretation was first proposed by physicist Hugh Everett III. In 1957, Everett's work was motivated by the need to reconcile the probabilistic nature of quantum mechanics with the idea that the universe behaves deterministically. According to classical physics, the future of a system is fully determined by its present state, but quantum mechanics, with its inherent randomness and uncertainty, seem to contradict this deterministic view. Everett suggested that the apparent randomness of quantum mechanics could be explained by the idea that all possible outcomes of a quantum event actually occur, but in separate parallel universes. Instead of a single outcome occurring when a measurement is made, the universe splits into multiple branches, with each branch corresponding to a different possible outcome. This allows for all possible outcomes to be realized, but in different versions of reality. For example, consider the classic double-slit experiment, which is a fundamental demonstration of quantum behavior. In this experiment, particles, like electrons, are fired at a barrier with two slits, and the pattern they create on a detector screen is observed. When not measured, the electrons behave like waves, passing through both slits at once and creating an interference pattern on the screen. However, when the electrons are measured, they act like particles, passing through one slit or the other, and the interference pattern disappears. In the many worlds interpretation, instead of the wave function collapsing when the electrons are measured, the universe splits into two branches, one where the electron goes through one slit, and another where it goes through the other. In each universe, the measurement appears to have yielded a different result, but both outcomes exist simultaneously in separate parallel worlds. How the many worlds interpretation works. In the many worlds view, the universe is constantly splitting into different branches, with each branch representing a different outcome of a quantum event. This occurs whenever a measurement or observation is made. If a person is involved in the observation, their consciousness would also split, experiencing one of the possible outcomes while the other branches exist in parallel, unseen but equally real. To understand this concept better, imagine a simple situation where you are about to flip a coin. According to quantum mechanics, until the coin is observed, it exists in a superposition of both heads and tails. The moment you observe the coin, the superposition collapses, and the coin is either heads or tails. In the many worlds interpretation, however, both outcomes occur simultaneously. One version of you experiences heads while another version experiences tails. Both versions of reality exist in parallel, with each observer in a different branch of the universe. These parallel universes are not just limited to quantum experiments involving individual particles. In theory, any decision or event in the universe that has multiple possible outcomes could lead to a branching of the universe. Each time an event occurs that has more than one possibility, the universe splits into multiple realities, each representing a different possibility. The result is a potentially infinite number of parallel universes. The implications of the many worlds interpretation. The many worlds interpretation has profound implications for our understanding of reality. If it is correct, then every possible outcome of every quantum event occurs in some branch of the universe. The universe is not a single linear reality, but an ever-expanding multiverse of parallel worlds, each with its own version of events. One of the most striking implications of the many worlds interpretation is that the universe is infinitely branching. Every decision you make, no matter how small, creates a new branch of reality. In one universe, you might choose one path, while in another, you make a completely different choice. Both outcomes coexist, but in separate realities. This could mean that there are infinite versions of you, each making different choices, experiencing different events, and living different lives. Furthermore, the many worlds interpretation implies that nothing is lost in the universe. Every possible outcome is realized in some branch, meaning that no matter what happens, every possible history is accounted for in a parallel universe. This view challenges the idea of a single unique timeline, suggesting instead that all possibilities coexist in a vast, interconnected web of realities. Criticism of the many worlds interpretation. Despite its fascinating implications, the many worlds interpretation has been the subject of considerable debate among physicists. One of the main criticisms is that the theory introduces an infinite number of unobservable universes, making it difficult to test or verify. While the theory is mathematically consistent with quantum mechanics, it lacks the ability to make direct predictions or provide empirical evidence for the existence of parallel worlds. This lack of observational evidence has led some physicists to consider the theory speculative, preferring other interpretations of quantum mechanics such as the Copenhagen interpretation, which argues that the wave function collapses into a single state upon measurement. Another criticism is that the many worlds interpretation implies an infinite number of universes with an infinite number of outcomes, many of which may be completely disconnected from our own. This raises the philosophical question of whether the idea of infinite parallel universes is meaningful or simply a theoretical artifact of quantum mechanics. Some argue that the theory is unnecessarily complicated and that simpler models may be more useful for explaining quantum phenomena. Testing the many worlds interpretation. One of the biggest challenges with the many worlds interpretation is that it is difficult to test. Since the theory posits that all possible outcomes occur in separate parallel universes, it is inherently unobservable. We cannot directly access or observe these alternate realities, making it hard to gather experimental evidence that supports the existence of parallel worlds. However, there are indirect ways in which the theory could be tested. For example, certain phenomena in quantum mechanics, such as interference patterns in the double-slit experiment, may provide evidence for the existence of multiple parallel realities. If the many worlds interpretation is correct, then the interference patterns observed in quantum experiments could suggest that particles are taking multiple paths simultaneously, effectively traveling through multiple realities. Additionally, cosmological observations may offer clues to the existence of parallel universes. Some physicists have suggested that if our universe is part of a multiverse, we might detect signs of other universes through their gravitational influence on our own. This could come in the form of subtle variations in the cosmic microwave background radiation or other anomalies in the structure of the universe. However, these ideas remain speculative, and direct evidence of parallel universes is still lacking. The role of parallel universes in popular culture. While the many worlds interpretation remains a theoretical idea in physics, the concept of parallel universes has captured the popular imagination for centuries. From science fiction literature to blockbuster movies, parallel universes have become a staple of storytelling, allowing characters to explore alternate realities and encounter versions of themselves in different timelines. In these fictional depictions, parallel universes often represent what could have been, alternate histories where events played out differently or where the laws of nature are distinct from our own. These universes serve as a playground for exploring the consequences of choices, the nature of free will, and the question of fate versus chance. The success of films like Sliding Doors, Doctor Strange in the Multiverse of Madness, and the Flash TV series attests to the enduring appeal of parallel universes as a way to explore the vastness of possibility. Conclusion: the many worlds interpretation and the nature of reality. The many worlds interpretation offers a fascinating glimpse into the possibility of parallel universes, suggesting that every quantum decision creates a branching of the universe, leading to the creation of multiple coexisting realities. While it challenges our traditional notions of determinism and free will, the theory provides a mathematical framework for understanding how parallel universes could exist within the quantum realm. However, the many worlds interpretation is still a topic of debate and is not without its criticisms. The theory's lack of direct observational evidence and its reliance on an infinite number of unobservable universes make it a difficult hypothesis to prove. Nevertheless, the idea of parallel universes remains one of the most intriguing and exciting concepts in modern physics, with the potential to revolutionize our understanding of reality and the nature of existence itself. As our understanding of quantum mechanics continues to evolve, so too will our exploration of parallel universes. Whether or not the many worlds interpretation is ultimately proven true, the concept of parallel universes will continue to inspire new questions, ideas, and possibilities about the nature of the cosmos and our place within it. One of the most exciting and mind-bending ideas related to parallel universes is the concept of wormholes. These hypothetical tunnels through space-time could provide a shortcut between distant regions of space, and in some interpretations, they might even allow for travel between different universes. If parallel universes do exist, could wormholes offer a bridge between them? Could we use wormholes not just to travel across space, but also to explore alternate realities and alternate versions of our own universe? In this chapter, we will explore the idea of wormholes, their theoretical basis in general relativity, and how they might relate to the existence of parallel universes. We will also discuss the potential role that wormholes could play in time travel, and whether they might provide a way for us to access other universes or dimensions. While wormholes remain speculative and unproven, they remain one of the most intriguing concepts in modern physics, with the potential to unlock new frontiers of understanding in both space and time. What is a wormhole? In the most basic terms, a wormhole is a hypothetical passage through space-time that could connect two distant points in the universe. It is often visualized as a tunnel with two ends, each located at separate points in space-time. These tunnels could, in theory, allow for faster-than-light travel, bypassing the intervening space between the two ends of the wormhole. Rather than traveling through the vast distances of space, an object or person could simply enter one end of the wormhole and instantly appear at the other end. Wormholes were first proposed as solutions to the equations of general relativity by physicists Albert Einstein and Nathan Rosen in 1935. The original formulation of a wormhole was known as an Einstein-Rosen bridge, and it was intended to describe a connection between two black holes. The term wormhole was coined later and has since become a staple in science fiction and theoretical physics. While the concept of a wormhole sounds like something out of a science fiction novel, it is grounded in real physics. General relativity describes the curvature of space-time, and it is through this curvature that wormholes might exist. If space-time can be curved in the right way, it may be possible to create a shortcut between two distant points in the universe, much like folding a piece of paper to connect two distant points with a hole. In general relativity, the concept of space-time, the four-dimensional continuum that combines the three dimensions of space with the one dimension of time, is fundamental. The geometry of space-time can be bent, warped, and distorted by the presence of massive objects. This bending of space-time is what causes the force of gravity. But space-time is not a rigid, fixed background. It is dynamic and can be altered in such a way that it might permit the formation of wormholes. Wormholes and parallel universes. The idea that wormholes could provide access to parallel universes is a compelling one. If parallel universes exist, they may exist in separate branches of space-time, each with its own unique history, physical laws, and outcomes. Wormholes might serve as a bridge between these universes, offering a way to travel between them. In this framework, a wormhole could connect two parallel universes that exist in different realities or dimensions. These universes could be nearly identical, with only slight differences in events or outcomes, or they could be radically different, governed by entirely distinct physical laws. A person or object entering a wormhole could, in theory, travel from one parallel universe to another, experiencing a completely different version of reality. The possibility of wormholes connecting parallel universes is closely tied to the idea of the multiverse. the theory that our universe is just one of many that exist simultaneously. The multiverse theory suggests that there could be an infinite number of universes, each with its own set of physical constants, laws, and histories. In this context, a wormhole could act as a gate between these universes, providing a way to travel from one universe to another. But how could wormholes function as bridges between universes? According to some theoretical models, wormholes could be linked to higher dimensional space, dimensions beyond the familiar three dimensions of space and one of time. In higher dimensional space, the geometry of space-time could allow for connections between separate universes where each universe is a distinct slice of space-time. A wormhole might connect one slice of space-time, one universe, to another, allowing for travel between them. Wormholes and time travel. One of the most exciting aspects of wormholes is their potential to facilitate time travel. If wormholes can connect two distant points in space-time, could they also connect different moments in time? In essence, could a wormhole act as a time machine, allowing an object or person to travel into the past or future? The idea of time travel via wormholes is grounded in the principles of general relativity, which allows for the curvature of space-time. If space-time is curved in such a way that 2 points in time are connected through a wormhole, then travel between those points could be possible. In theory, this could enable a form of closed time-like curves, CTCs, where an object or person enters the Ibanoleo wormhole and arrives at an earlier or later point in time. The idea of time travel via wormholes is not new. It has been discussed by physicists such as Kip Thorne and others who have explored the possibility of creating a traversable wormhole that could connect different points in time. In the simplest case, a wormhole could allow a person to travel forward in time by entering one end of the wormhole and emerging at a point in the future. The time dilation effects of the wormhole would ensure that time passes differently for the traveler inside the wormhole relative to someone outside. In a more speculative scenario, a wormhole could be used to travel back in time. If the two ends of the wormhole are connected to different points in time, a person could enter the wormhole in the present and emerge at a point in the past. However, this scenario raises serious paradoxes, such as the famous grandfather paradox, in which a time traveler could potentially alter events in the past, creating logical contradictions. These paradoxes are still a major topic of debate among physicists and philosophers, with some proposing that the universe would self-correct to prevent such contradictions from occurring. Theoretical models of wormholes and time travel. There are several theoretical models that suggest how wormholes might be used for time travel. One of the most famous models is the Einstein-Rosen bridge, which describes a non-traversable wormhole, a wormhole that connects two black holes but cannot be used for travel. The problem with this model is that the wormhole would collapse before anything could pass through it. To make a wormhole traversable, we would need to stabilize it and prevent its collapse. This is where the concept of exotic matter with negative energy comes in. Exotic matter is a hypothetical form of matter that has negative energy density, meaning that it has the opposite effect of regular matter. While regular matter causes space-time to curve in a way that attracts objects, gravity, exotic matter would curve space-time in the opposite direction, effectively pushing objects apart. If such exotic matter could be harnessed, it might be used to stabilize a wormhole, preventing it from collapsing under the intense gravitational forces at its ends. This would theoretically allow for safe travel through the wormhole, potentially even for time travel. Another theoretical model of time travel via wormholes comes from the concept of rotating black holes, or Kerr black holes. These black holes, which rotate rapidly, create a region of space-time that could, in theory, form a closed time-like curve. In this model, an object that falls into a rotating black hole could travel backward in time, emerging at an earlier point in space-time. This is still purely theoretical, and the extreme conditions near a black hole make this type of time travel highly speculative. Challenges to creating wormholes. While the theoretical models for wormholes and time travel are fascinating, there are significant challenges that must be overcome before wormholes could become a practical means of travel. One of the primary obstacles is the need for exotic matter with negative energy. Without this form of matter, a wormhole would collapse almost immediately, preventing anything from passing through. Currently, exotic matter has never been observed, and there is no known way to create it. Another challenge is the immense energy requirements for creating and stabilizing a wormhole. The energy required to manipulate space-time on such a large scale is far beyond anything humanity can currently produce. In fact, the energy requirements to create a wormhole or to travel at relativistic speeds, close to the speed of light, would likely exceed the total energy available in our entire galaxy. Additionally, the physical dangers of traveling through a wormhole or near a black hole would be extreme. The gravitational forces near a black hole, for example, would stretch and distort objects in a process known as spaghettification, making it impossible for anything to survive the journey. Even if a stable wormhole could be created, the risks involved in using it for time travel would be enormous. Wormholes and the possibility of parallel universes. If wormholes can exist and are stable enough to allow for travel, could they provide access to parallel universes? In the framework of the multiverse theory, wormholes might serve as conduits between different universes, each with its own set of physical laws and realities. A person entering a wormhole might emerge in a parallel universe where the events of history unfolded differently or where the laws of physics are radically different from our own. This idea is highly speculative and has not been tested in any way, but it offers an intriguing possibility for the connection between wormholes and parallel universes. If parallel universes do exist, wormholes might provide the only practical means of accessing them. However, this would also raise significant questions about the nature of reality and the implications of interacting with alternate worlds. Conclusion: wormholes as bridges to parallel universes. The concept of wormholes offers a fascinating and speculative way to connect parallel universes and explore time travel. While the theoretical underpinnings of wormholes are grounded in the equations of general relativity, the challenges involved in creating and stabilizing wormholes are immense. The need for exotic matter, the energy requirements, and the physical dangers of traveling through space-time make the creation of a time machine via wormholes a daunting task. However, the idea that wormholes could provide access to parallel universes and allow for time travel is a tantalizing possibility. Whether or not wormholes will ever be practical or proven to exist, they continue to be one of the most intriguing concepts in modern physics, offering a glimpse into the future of space-time exploration and our understanding of the universe. In the next chapter, we will delve deeper into the multiverse theory and explore how different versions of reality might exist within the framework of parallel universes. Are we truly living in one of many universes? And if so, what does that mean for our understanding of reality? The concept of parallel universes takes on a more complex and intriguing dimension when we introduce the multiverse theory. The idea that there are potentially infinite universes, each with its own set of physical laws, constants, and histories. These universes might exist side by side, completely separate from each other, or they could be interwoven in ways we do not yet understand. The multiverse theory suggests that the universe we observe is not the only one that exists, and that reality itself is far more vast, complex, and varied than we can imagine. In this chapter, we will explore the multiverse theory in detail, examining the different models that have been proposed to explain the existence of parallel universes. We will look at the scientific theories that support the multiverse hypothesis, the implications of an infinite number of universes, and the potential for alternate realities where different versions of history have unfolded. We will also explore some of the philosophical and existential questions that arise from the possibility of an infinite multiverse. What is the multiverse theory? The multiverse theory suggests that our universe, with its particular laws of physics, constants, and history, is just one of many universes in a larger, more complex reality. According to this idea, there could be an infinite number of universes, each with its own unique characteristics. These universes may be similar to ours, with only slight differences, or they may be radically different, governed by completely different physical laws and constants. The multiverse theory challenges the traditional view of the universe as a singular, unique entity. Instead of a single universe with a fixed history, the multiverse suggests a vast and potentially infinite collection of universes, each with its own version of reality. In this model, our universe is just one bubble in an ocean of countless other bubbles, each representing a separate universe. The concept of the multiverse is not new, but it has gained increasing attention in modern physics, especially in relation to quantum mechanics, cosmology, and string theory. While the multiverse theory is still speculative and lacks definitive observational evidence, it offers a possible framework for explaining some of the most fundamental questions in physics and cosmology. The different models of the multiverse. There are several different models of the multiverse, each based on different theories in physics. These models vary in their assumptions about the nature of parallel universes and the way they interact with one another. Some of the most prominent models include 1. The bubble multiverse, inflationary multiverse. One of the most widely discussed models of the multiverse comes from the theory of cosmic inflation. Cosmic inflation is a theory proposed by physicist Alan Guth in the 1980s to explain the rapid expansion of the universe in the moments after the Big Bang. According to inflationary theory, the early universe underwent an extremely rapid period of exponential expansion, which smoothed out irregularities and set the stage for the formation of galaxies and stars. The inflationary multiverse is a natural extension of cosmic inflation. According to this model, inflation does not occur just once. It happens repeatedly in different regions of space. Each time inflation occurs, it creates a new bubble of space-time, which becomes its own universe with its own physical properties. These bubbles are often referred to as pocket universes, and each one could have different physical constants, laws of nature, and histories. The multiverse, in this case, consists of a vast number of these bubble universes, each with its own version of reality. In this model, the universe we observe is just one bubble in a much larger multiverse, where each bubble represents a different universe with its own unique characteristics. Some of these universes could be very similar to ours, with similar physical constants and laws, while others could be completely different, with different forms of matter, different physical constants, or even completely different laws of physics. 2. The many worlds interpretation of quantum mechanics. The many worlds interpretation, MWI, of quantum mechanics, proposed by physicist Hugh Everett III in 1957, also suggests the existence of parallel universes, but in a very different way. According to the many worlds interpretation, every quantum event that has multiple possible outcomes leads to the splitting of the universe into different branches, with each possible outcome occurring in a separate universe. For example, consider the famous double-slit experiment in quantum mechanics, in which a particle like an electron is sent through two slits. When the particle is not observed, it behaves as a wave and passes through both slits simultaneously, creating an interference pattern. However, when the particle is observed, it behaves like a particle and goes through only one slit. In the many worlds interpretation, both outcomes occur. In one universe, the electron goes through the left slit, and in another universe, it goes through the right slit. Every quantum event that has multiple possible outcomes creates a new branch of reality, with each branch representing a different version of the universe. This interpretation leads to the idea of an infinite number of universes, each representing a different outcome of every quantum decision. The many worlds interpretation suggests that all possibilities are realized, but in separate parallel universes, each of which evolves independently from the others. In this view, the multiverse is not a collection of universes that coexist in the same space, but rather a branching tree of realities, where every quantum event leads to the creation of new parallel universes. 3. The string theory. Multiverse. String theory is a theoretical framework in physics that attempts to reconcile quantum mechanics with general relativity. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings that exist in higher dimensional space. These strings vibrate at different frequencies, giving rise to the various fundamental forces and particles that make up the universe. One of the key predictions of string theory is that the universe has more than the three dimensions of space and one of time that we observe. In fact, string theory predicts the existence of extra dimensions, up to 10 or 11 dimensions, depending on the version of the theory. These extra dimensions could be compactified or curled up on scales too small to detect. The way these dimensions are compactified could influence the properties of the universe, including the strength of gravity, the nature of particles, and the constants of nature. The string theory multiverse arises from the idea that there are many possible ways in which the extra dimensions could be compactified. In each case, the compactification of dimensions leads to different physical properties in each universe. As a result, the string theory multiverse consists of a vast number of universes, each with different physical laws, constants, and structures, depending on how the extra dimensions are shaped. Some versions of string theory suggest that the multiverse is not just a collection of universes, but that the different universes are connected by wormholes or other structures, allowing for the possibility of interaction between them. In this view, our universe is just one of many possible universes that could have emerged from the same underlying physical principles, but each universe has its own distinct set of properties. 4. The landscape multiverse. The landscape multiverse is a concept derived from string theory and the idea of vacuum energy. In this model, the different possible vacuum states, or vacua, of string theory correspond to different universes. Each universe in the landscape multiverse has its own set of physical laws and constants, determined by the specific vacuum state in which it exists. The landscape multiverse is sometimes called the anthropic multiverse because it suggests that the reason our universe has the particular properties that allow for life is simply that there are an infinite number of universes, and in one of them, the conditions just happen to be right for the emergence of life. This idea is often used to explain the fine-tuning problem in cosmology, the question of why the constants of nature seem to be perfectly calibrated to allow life. According to the landscape multiverse, the answer is that there are an infinite number of universes with different properties, and we happen to live in one where life can exist. Implications of the multiverse theory. The multiverse theory has profound implications for our understanding of reality, cosmology, and even philosophy. If the multiverse theory is correct, it suggests that our universe is not the only one, and that reality itself is far more vast, complex, and varied than we can comprehend. The existence of multiple universes opens up a whole new realm of possibilities, both scientifically and philosophically. The anthropic principle. One of the most widely discussed implications of the multiverse theory is the anthropic principle. This principle suggests that the physical constants and laws of nature in our universe are finely tuned to support life. The anthropic principle posits that the reason the universe appears so perfectly suited for life is simply because we exist to observe it. In other words, the universe must have the properties that allow for life because we are here to observe it. According to the landscape multiverse, the reason for this fine-tuning is that there are an infinite number of universes, each with different properties. Some universes might have physical constants that are not conducive to life, while others might have conditions that allow for life to thrive. The anthropic principle suggests that we find ourselves in a universe that supports life simply because, out of the infinite number of possible universes, one had the right conditions for life to emerge. Existence of infinite versions of reality. Another profound implication of the multiverse theory is the idea that there are infinite versions of reality, each with its own set of possibilities. Every decision, every quantum event could create a new branch of reality, resulting in a vast and potentially infinite number of parallel universes. This means that every possible outcome of every event, from the smallest quantum decision to the largest cosmic event, could exist in some universe. In a sense, the multiverse theory suggests that anything that can happen does happen somewhere in the multiverse. If the multiverse is infinite, it is likely that every possible version of events is realized in some universe, leading to a vast and unimaginable array of parallel realities. Conclusion: The multiverse. Infinite universes, infinite possibilities. The concept of the multiverse is one of the most exciting and speculative ideas in modern physics. Whether it is through cosmic inflation, the many worlds interpretation of quantum mechanics, string theory, or the landscape multiverse, the idea that our universe is just one of many offers a new perspective on reality itself. The multiverse challenges our understanding of space, time, and existence, suggesting that the universe we see is just a small part of a much larger and more complex reality. While the multiverse theory is still speculative and lacks definitive observational evidence, it provides a framework for understanding some of the most fundamental questions in cosmology and physics. As our understanding of the universe continues to evolve, the multiverse theory may one day be tested through new discoveries in quantum mechanics, cosmology, and particle physics. For now, the concept of parallel universes remains a tantalizing possibility, one that forces us to reconsider our place in the cosmos and the nature of reality itself. Whether or not the multiverse exists, the pursuit of this idea continues to inspire scientists, philosophers, and explorers of the unknown, pushing the boundaries of human knowledge and imagination. As we delve deeper into the mysteries of the universe, one of the most provocative and unsettling ideas that has emerged in recent years is the simulation hypothesis. The theory suggests that our entire universe, from the stars in the sky to the molecules that make up our bodies, might be nothing more than a computer simulation created by an advanced civilization. Could we, as conscious beings, be living in a virtual world, unaware that our entire reality is a construct of algorithms and artificial intelligence? In this chapter, we will explore the simulation hypothesis, examining its origins, the scientific theories behind it, and the implications it has for our understanding of reality. We will also discuss the philosophical questions raised by the idea of living in a simulated world, from the nature of consciousness to the question of what it means to be real. Is the universe we experience truly the only one? Or could we be living in a simulation within a larger, more complex multiverse? What is the simulation hypothesis? The simulation hypothesis proposes that our entire universe, including everything we experience, could be a computer simulation created by an advanced civilization. According to this theory, our reality, with all of its physical laws, constants, and fundamental structures, could be nothing more than a highly sophisticated virtual construct designed to mimic the real world. This idea is based on the assumption that as civilizations advance technologically, they may develop the ability to simulate entire universes. These simulations could be so detailed and complex that the inhabitants of these simulations would not be able to tell that their world is artificial. In essence, the simulation hypothesis suggests that what we perceive as the real world could be an illusion, created by a superintelligent entity or civilization. The simulation hypothesis is often associated with the concept of digital consciousness, the idea that consciousness, or the experience of being alive, could exist within a digital system. Just as we experience a virtual world when we play video games or interact with simulations on a computer, the theory suggests that our consciousness might exist within a digital environment, interacting with and perceiving the simulated world around us. The simulation hypothesis is not just the stuff of science fiction. It has gained serious attention in the scientific community, especially among philosophers, cosmologists, and physicists who have explored the potential implications of a simulated reality. The origins of the simulation hypothesis. The simulation hypothesis was popularized in part by the work of philosopher and futurist Nick Bostrom, who published a groundbreaking paper in 2003 titled, "Are You Living in a Computer Simulation?" In his paper, Bostrom argued that one of three possibilities must be true. 1. Human civilization is unlikely to reach a level of technological development capable of creating simulations of entire universes. 2. If such a level of technological development is possible, civilizations are unlikely to create simulations of their ancestors or the past. 3. We are almost certainly living in a computer simulation. Bostrom's argument is based on the assumption that if a civilization becomes advanced enough to simulate entire worlds with high fidelity, it would likely create many such simulations. Given the vast computational power required to simulate an entire universe, the number of simulated worlds would far outnumber the number of real worlds. Therefore, the probability that we are living in one of these simulations becomes very high. Bostrom's paper sparked a debate within the scientific community, with many philosophers and scientists exploring the possibility of living in a simulated reality. His work raised important questions about the nature of reality, consciousness, and the limits of human knowledge. If we are living in a simulation, could we ever prove it? And if we were able to prove it, what would that mean for our understanding of existence? The technological foundations of the simulation hypothesis. The idea of a simulated universe relies on the assumption that an advanced civilization could possess the computational power to simulate an entire universe, complete with all of its physical laws, interactions, and events. In order to create a simulation as complex as our universe, this civilization would need to be capable of simulating not just individual particles, but entire galaxies, stars, and even the most intricate interactions between subatomic particles. This would require an extraordinary amount of computational resources, far beyond anything humanity can currently achieve. However, as our technology continues to advance, we are already making strides in fields like artificial intelligence, AI, quantum computing, and virtual reality that might one day provide the foundation for creating such simulations. In particular, the concept of quantum computing, which leverages the principles of quantum mechanics to process information in ways that classical computers cannot, could play a crucial role in the development of simulations of entire universes. Quantum computers are capable of processing vast amounts of data simultaneously, making them a potential tool for creating highly complex simulations. Moreover, as AI and computational power continue to evolve, it's possible that future civilizations could develop hyper-intelligent systems capable of simulating entire worlds with incredible precision. These systems could create simulations so sophisticated that the inhabitants of those worlds would experience them as fully real. In essence, if humanity or some future civilization were able to harness the full potential of computational power, it might be able to create universes indistinguishable from the real world. And if such simulations could be created, then the possibility of living in one becomes a topic worth serious consideration. Can we detect a simulation? One of the most intriguing questions raised by the simulation hypothesis is whether it would be possible to detect that we are living in a simulation. If our reality is indeed a simulation, we would expect certain signs or anomalies that reveal the artificial nature of our world. One potential clue comes from the study of quantum mechanics and the behavior of subatomic particles. Some physicists and theorists have suggested that if our universe is a simulation, there might be discrete limits to the resolution of space-time, much like the pixels in a computer screen. These limits would represent the graininess of the simulation, where space-time is not smooth and continuous, but rather composed of tiny discrete units. The idea of a pixelated universe suggests that if we were able to observe the universe at extremely small scales, we might detect a kind of lattice structure or irregularity in the fabric of space-time. This could be evidence that our universe is computationally constructed, with each pixel or unit of space-time representing a basic element in the simulation. Another potential clue might come from the fine-tuning of the universe. The fundamental constants of nature, such as the strength of gravity, the charge of the electron, and the cosmological constant, appear to be precisely calibrated to allow for the existence of life as we know it. Some have suggested that this fine-tuning could be the result of a simulation where the parameters are carefully adjusted to ensure the universe behaves in a way that supports life. This could be analogous to the way a game developer adjusts the rules and physics of a video game to create a specific experience. While these ideas are still speculative and unproven, they represent possible avenues of investigation for detecting a simulated reality. However, proving the simulation hypothesis remains an incredibly difficult task, and we may never be able to directly detect whether we are living in a simulation. The very nature of a simulation means that it could be designed to be indistinguishable from reality, making it nearly impossible to detect through conventional means. Philosophical implications of the simulation hypothesis. The simulation hypothesis raises profound philosophical questions about the nature of reality, consciousness, and existence itself. If we are living in a simulation, does that mean that our lives and experiences are somehow less real than those in a base reality? And if our reality is a simulation, who or what created it, and why? One key question is whether consciousness can exist within a simulation. If our thoughts, emotions, and experiences are generated by a computer program, does that mean our consciousness is an artificial construct, or is it real in its own right? Philosophers have long debated the nature of consciousness, but the simulation hypothesis introduces a new wrinkle. Could our consciousness be a program running on a super-intelligent computer? If so, does that change our understanding of what it means to be alive? Another question involves the ethical implications of living in a simulation. If we are living in a computer program, what does that say about our autonomy and free will? Are we simply following predetermined paths with our choices and actions governed by the parameters of the simulation? Or is there room for genuine free will within a simulated world? The simulation hypothesis also touches on existential concerns about the meaning of life. If we are living in a simulation, does that mean our existence has no greater purpose and that we are merely part of a larger experiment or game? Or does our subjective experience of reality give our lives meaning, regardless of whether the world around us is real or simulated? The impact of the simulation hypothesis on science and technology. The simulation hypothesis also has significant implications for the future of science and technology. If we are indeed living in a simulated reality, then the laws of physics that govern our universe could be artificially constructed by the creators of the simulation. This raises the possibility that we could one day break the rules of our universe, just as a character in a video game can break the rules of the game world. For example, in a simulated reality, it might be possible to hack the system or manipulate the underlying code that governs the universe. This could lead to the development of new technologies or the ability to perform feats that are currently considered impossible, such as faster-than-light travel or time manipulation. In this sense, the simulation hypothesis challenges our understanding of the limits of science and technology. If our universe is a simulation, then the potential for innovation and discovery could be virtually unlimited, limited only by the capabilities of the simulation itself. Conclusion. Are we living in a simulation? The simulation hypothesis is a provocative and thought-provoking idea that raises fundamental questions about the nature of reality, consciousness, and existence. While the idea of living in a computer, simulation may seem like science fiction, it is based on serious philosophical and scientific reasoning. As we continue to explore the boundaries of physics, quantum mechanics, and artificial intelligence, the question of whether we are living in a simulation remains open. Whether or not we will ever be able to prove the simulation hypothesis remains uncertain. The complexity of the universe and the limitations of our current technology make it difficult to detect whether our reality is artificial. However, the possibility that we could be living in a simulation has profound implications for our understanding of reality, free will, and the meaning of life. As we continue to probe the mysteries of the cosmos and our place within it, the simulation hypothesis offers a tantalizing glimpse into the nature of the universe and the future of human discovery. As our understanding of the universe deepens, some of the most mind-boggling ideas arise not from the classical models of physics, but from cutting-edge theories that challenge our perceptions of reality. One such theory, known as the holographic principle, proposes that the universe we experience, the three-dimensional reality that feels so solid and real, may not be as it seems. According to the holographic principle, what we perceive as a three-dimensional world could actually be a projection of information encoded on a two-dimensional surface, much like a hologram. This idea is deeply connected to the world of string theory, quantum mechanics, and black holes, and it has the potential to completely change our understanding of space, time, and the nature of the universe. If the universe is indeed a hologram, this opens up fascinating new questions about the fundamental nature of reality, the possibility of parallel universes, and whether our perceptions of the world around us are an illusion. In this chapter, we will explore the holographic principle, its origins, the scientific theories that support it, and the profound implications it has for our understanding of the universe. We will also examine how this principle could relate to the concept of parallel universes, and whether it suggests that our universe is just one of many possible projections in a higher dimensional space. What is the holographic principle? At its core, the holographic principle is the idea that the entire universe, or at least the information contained within it, can be described in two dimensions, and that our three-dimensional experience is a projection from this two-dimensional reality. This concept is drawn from string theory and the study of black holes, and was first proposed in the 1990s by physicist Juan Maldacena in what has become known as the AD-CFT correspondence, anti-de Sitter conformal field theory correspondence. Maldacena's groundbreaking work suggested that certain types of physical theories, which describe the fundamental forces of nature, can be thought of as being equivalent to lower dimensional theories. This equivalence suggests that the detailed, complex interactions that occur in a universe with many dimensions might be described in terms of simpler, lower-dimensional systems. In this view, the three-dimensional experience of the universe we perceive could be a projection of the information encoded in two dimensions, much like how a hologram is a three-dimensional image encoded on a flat two-dimensional surface. To understand this concept more clearly, imagine a hologram, a two-dimensional surface, like a laser-etched film, that when illuminated creates a three-dimensional image. In the same way, the holographic principle suggests that the three-dimensional universe we observe could be an image created by information encoded in a two-dimensional surface, perhaps at the cosmic horizon or the boundary of the universe. This idea challenges our intuition and understanding of the physical world. Our everyday experiences tell us that space is three-dimensional, that objects have length, width, and height. Yet, the holographic principle proposes that this three-dimensional reality is not fundamental, but a projection of information from a lower dimensional space. If true, this could imply that the universe is fundamentally different from how we perceive it, and that our experiences of space and time may be illusions, rooted in something more abstract. Origins of the holographic principle. The holographic principle originated from the study of black holes, some of the most mysterious and extreme objects in the universe. The key insight came from the work of physicists Jacob Bekenstein and Stephen Hawking, who in the 1970s developed a theory about the entropy of black holes. They found that the amount of information that could be contained within a black hole is proportional to the surface area of its event horizon, the boundary beyond which nothing, not even light, can escape, rather than the volume of the black hole. This result, known as the Bekenstein-Hawking entropy, suggested that the physical laws of the universe might not be fundamentally tied to the three-dimensional volume of space, but rather to the two-dimensional surface that bounds space. This was a surprising finding, as it indicated that information about a black hole could be encoded on its surface, even though the hole itself is a three-dimensional object. The insight that information could be encoded on a surface rather than in three-dimensional space led to the holographic principle. In essence, the principle suggests that just as black holes encode their information on their event horizon, the entire universe may encode all its information on a two-dimensional surface, which could be at the boundary of the universe itself. This idea implies that the three-dimensional space in which we live is a projection from a two-dimensional surface, much like a hologram. The holographic principle was further developed in the 1990s with the introduction of the AD-CFT correspondence by Juan Maldacena. This correspondence provided a concrete framework for understanding the holographic principle in the context of string theory, a theoretical framework that attempts to unify all of the fundamental forces of nature. Maldaceno's work suggested that certain kinds of physical theories with gravity, described by anti-de Sitter spaces, are mathematically equivalent to quantum field theories without gravity, described by conformal field theories, in one lower dimension. This idea became the basis for the holographic principle, as it suggested that the three-dimensional universe we observe could be described by a theory in two dimensions. The holographic universe and parallel universes. If the universe is indeed a hologram, with its three-dimensional reality being a projection of information encoded in two dimensions, this raises fascinating possibilities for the existence of parallel universes. The holographic principle suggests that our universe may not be a unique, isolated entity, but rather one of many possible projections that emerge from a higher dimensional space. One of the most intriguing aspects of the holographic principle is its potential connection to the multiverse theory. In a multiverse framework, there could be many universes, each with different physical laws and constants. If our universe is a holographic projection, it could be just one of many possible projections from a higher dimensional space. Each of these universes could represent a different realization of the same underlying information, a different way of encoding the fundamental laws of nature. In this view, the existence of parallel universes is not just a theoretical possibility, but a natural consequence of the holographic principle. If our universe is a hologram, then it's likely that there are other universes, each a different projection of the same information, existing alongside ours. These universes could be similar to ours, with only slight differences in their physical laws and constants, or they could be radically different, governed by entirely different sets of rules. Moreover, the holographic multiverse suggests that the boundaries between different universes may not be as fixed as we think. If our universe is just a projection, then the boundaries between different universes may not be solid walls, but rather permeable surfaces that allow for interactions or connections between universes. This could open the door to new possibilities for inter-universe travel or the exchange of information between parallel realities. Black holes, entropy, and the holographic universe. One of the most exciting aspects of the holographic principle is its connection to black holes and the nature of entropy. As we mentioned earlier, the work of Bekenstein and Hawking showed that the entropy of a black hole is proportional to the area of its event horizon, not the volume inside it. This discovery led to the idea that black holes are not just massive objects that trap matter, but are also information storage devices, encoding vast amounts of data on their surface. In the context of the holographic principle, this means that the universe itself may be a kind of giant black hole, with the information about everything that happens inside it encoded on a two-dimensional surface, the boundary of the universe. This leads to a radical shift in how we think about space and time. Instead of viewing the universe as a three-dimensional volume with space and time as fundamental aspects of its structure, the holographic principle suggests that space and time may be emergent properties arising from a deeper, more fundamental reality. The idea of a holographic universe has profound implications for the nature of information. If all of the information about our universe is encoded on a two-dimensional surface, then this suggests that the universe itself could be thought of as a kind of simulation or information processing system. In this view, the universe is not a continuous physical entity, but a computational process that emerges from the interplay of information. This idea resonates with concepts found in quantum information theory and computational physics, which treat the universe as a complex network of interacting bits of information. If space and time are emergent properties, then it's possible that the entire universe is the result of an underlying informational process, akin to a computer simulation or hologram. The implications for our understanding of reality. The holographic principle has profound implications for our understanding of the universe and our place in it. If the universe is indeed a projection of two-dimensional information, then much of what we perceive as reality may be an illusion. The three-dimensional world that we experience, with its vast distances, massive objects, and complex interactions, could be an emergent property, a projection from a deeper layer of reality that we cannot directly observe. This raises fundamental questions about the nature of consciousness and perception. If our experiences are simply projections, then what does it mean to be conscious? Are we merely observing a simulation of reality, or is our consciousness the product of the underlying information that drives the projection? These questions challenge our understanding of existence itself, suggesting that what we perceive as real may not be the true nature of reality. Moreover, the holographic principle raises the possibility that space and time are not fundamental properties of the universe, but emergent phenomena. If space-time is a projection, then it might be possible to transcend it, opening up new possibilities for exploring the universe, understanding its fundamental structure, and even manipulating the fabric of reality. Challenges and criticisms of the holographic principle. While the holographic principle offers an elegant and compelling framework for understanding the universe, it is still a speculative theory that faces significant challenges. One of the biggest criticisms of the holographic principle is that it is difficult to test. Since the idea suggests that the universe we experience is a projection, it is hard to devise experiments that could directly confirm or disprove the theory. Moreover, the holographic principle challenges deeply ingrained assumptions about space, time, and reality. The idea that space-time is not fundamental but emergent is a radical departure from classical physics and has yet to be fully accepted by the scientific community. The lack of direct evidence for the holographic principle, combined with the inherent complexity of testing it, means that it remains a speculative and controversial idea in modern physics. Conclusion: the holographic universe and our place in it. The holographic principle offers a bold and fascinating vision of the universe as a projection, where our three-dimensional reality is an emergent property of two-dimensional information. While the theory is still speculative, it has profound implications for our understanding of space, time, and reality itself. If the universe is indeed a hologram, then we are living in a world that is far more complex and mysterious than we can imagine. The holographic principle also opens up intriguing possibilities for parallel universes, suggesting that our universe might be just one of many projections in a higher dimensional space. Whether or not the holographic principle is ultimately proven to be true, it challenges our deepest assumptions about the nature of reality and invites us to look at the universe in a completely new way. As our understanding of the universe continues to evolve, the holographic principle remains one of the most exciting and provocative ideas in modern physics. It forces us to reconsider the very fabric of reality and the nature of the cosmos, and it reminds us that the universe, in all its complexity, may be far more mysterious and wondrous than we ever imagined. When we think about parallel universes and alternate realities, it's easy to imagine them as distinct and isolated from one another, existing independently in their own domains. However, some of the most compelling theories in modern physics suggest that parallel universes could be interconnected, possibly linked through string theory, one of the most advanced and complex frameworks in theoretical physics. String theory, which seeks to unify all the forces of nature, offers a potential explanation for how multiple universes might coexist within a larger multiverse. In this chapter, we will delve into string theory and how it connects to the idea of parallel universes. We will explore how string theory attempts to explain the fundamental building blocks of reality, the potential for extra dimensions, and the role that these concepts might play in the existence of multiple universes. We will also examine how string theory's predictions could offer a new perspective on the multiverse, possibly suggesting ways in which parallel universes might interact or overlap with each other. What is string theory? At its core, string theory is a theoretical framework that attempts to explain the fundamental constituents of the universe by proposing that the most basic building blocks of nature are not point-like particles, as previously thought, but vibrating one-dimensional objects known as strings. These strings can vibrate at different frequencies, and the different modes of vibration correspond to different types of particles. In traditional particle physics, particles like electrons and quarks are considered to be point-like objects with no internal structure. However, string theory suggests that these particles are actually made up of tiny strings, which are so small that they cannot be directly observed with current technology. The idea is that each particle's properties, such as its mass, charge, and spin, are determined by how its string vibrates. String theory was initially developed to explain the force of gravity and to reconcile general relativity, which governs large-scale phenomena like gravity, with quantum mechanics, which governs the subatomic world. One of the key successes of string theory is that it naturally incorporates the idea of gravity into the quantum framework, something that previous attempts to unify gravity with quantum mechanics had failed to achieve. However, string theory is not just limited to explaining the fundamental forces of nature. It also introduces the concept of extra dimensions. These dimensions are crucial to understanding how string theory can accommodate multiple universes and how they might be connected. Extra dimensions and the multiverse. One of the most striking predictions of string theory is the existence of extra dimensions beyond the familiar three dimensions of space, length, width, and height, and one of time. According to string theory, the universe might have as many as 10 or 11 dimensions, depending on the version of the theory. These extra dimensions are thought to be compactified, or curled up, on scales so small that they are effectively invisible to us. In most versions of string theory, the additional dimensions are theorized to be compactified into tiny shapes known as Calabi-Yau manifolds. These shapes are incredibly intricate and complex, and they allow for the existence of multiple hidden dimensions of space-time. While we perceive only the 4 dimensions that we can directly observe, 3 of space and 1 of time, string theory suggests that there are many more dimensions beyond our perception, hidden within the fabric of space. These extra dimensions could have profound implications for the multiverse theory. If the universe we experience is just one of many possible realities, these additional dimensions could provide a way for different universes to exist side by side, each with its own set of physical laws and constants. The multiverse theory suggests that these universes could be separated by the additional dimensions predicted by string theory, which would allow for the possibility of universes that are separated in higher dimensional space. According to some models of the multiverse, each possible configuration of the extra dimensions could give rise to a different universe. Each universe would have its own version of reality, with different laws of physics, constants, and structures, depending on how the extra dimensions are compactified. In this sense, string theory's extra dimensions could serve as a foundation for a multiverse, with each universe in the multiverse corresponding to a different way of compactifying the extra dimensions. The landscape multiverse and string theory. One of the key ideas that emerge from string theory and its extra dimensions is the concept of the landscape multiverse. The landscape multiverse is based on the idea that the extra dimensions in string theory can be compactified in an almost infinite number of ways, each leading to a different physical universe. In this framework, the different configurations of the extra dimensions, the different ways they can be shaped, correspond to different possible vacuum states of string theory, each of which would give rise to a distinct universe. The landscape multiverse suggests that the reason our universe has the particular properties we observe, such as the strength of gravity, the charge of elementary particles, and the cosmological constant, is simply due to the specific configuration of the extra dimensions in our universe. If the extra dimensions could be compactified in a different way, we would end up with a different set of physical laws and constants. Some of these universes could be very similar to ours, while others could be radically different, with completely different laws of physics or even different types of matter. This idea is supported by the fact that string theory predicts a vast number of possible solutions, each corresponding to a different configuration of the extra dimensions. These solutions are sometimes referred to as the string theory landscape, and it's estimated that there could be up to 10,500 different possible solutions, each corresponding to a different universe in the multiverse. This gives rise to an incredibly large number of possible universes, each with its own unique set of properties. The landscape multiverse offers a potential solution to the fine-tuning problem in cosmology. which refers to the fact that the constants of nature in our universe appear to be perfectly calibrated for the existence of life. If the multiverse is real, then it's not surprising that we find ourselves in a universe that is fine-tuned for life. We live in one of the universes where the conditions happen to be right. In other universes, the conditions may not support life, but the sheer number of possible universes ensures that life could arise in at least one of them. Could parallel universes be linked through string theory? String theory offers a potential framework for connecting parallel universes, though this idea remains speculative and highly theoretical. If multiple universes exist, they could be connected through the extra dimensions predicted by string theory. These extra dimensions might provide the space in which different universes coexist, each with its own set of physical laws and constants. One possibility is that wormholes, as discussed in earlier chapters, could serve as the conduits between different universes. Wormholes are hypothetical tunnels in space-time that could connect distant regions of the universe, or potentially even separate universes in the multiverse. In string theory, the extra dimensions might provide the pathway for these wormholes to connect universes, allowing for the exchange of information or even the potential for travel between different realities. Another possibility is that the landscape multiverse could be interconnected through the extra-dimensional landscape of string theory. Each universe in the multiverse could be thought of as a different configuration of the extra dimensions, and there might be ways in which these configurations could interact or overlap. However, these interactions would likely be subtle, and the universes would remain largely separate from one another, governed by their own unique sets of laws and physical constants. The concept of a connected multiverse through string theory suggests that parallel universes might not be entirely isolated. There could be subtle interactions or even communication between them, potentially providing insights into the fundamental nature of reality. However, these ideas remain speculative, as we do not yet have the technology or understanding to test these theories. Challenges and criticisms of string theory and the multiverse. While string theory and the multiverse offer a tantalizing framework for understanding parallel universes, these ideas face significant challenges. One of the main criticisms of string theory is that it is highly mathematical and difficult to test experimentally. The extra dimensions predicted by string theory are believed to be so small that they cannot be observed directly with current technology. This makes it difficult to gather empirical evidence to support or refute the theory. Similarly, the idea of a multiverse, with potentially an infinite number of universes, each with its own set of laws, raises philosophical questions about the nature of reality and the testability of these universes. If parallel universes are completely disconnected from each other, then how can we ever know if they exist? Some physicists argue that the multiverse hypothesis is too speculative and lacks predictive power, while others see it as a natural extension of string theory and an important avenue of research. Another challenge is the fine-tuning required in string theory. While string theory offers a potential framework for the multiverse, it relies on specific assumptions about the nature of extra dimensions, and there are many possible configurations of these dimensions. Some critics argue that the multiverse hypothesis is overly reliant on these assumptions and may not be the most fruitful approach to understanding the fundamental nature of reality. Conclusion: string theory and the multiverse, a new perspective on parallel universes. String theory provides a rich and complex framework for understanding the fundamental structure of the universe and the possibility of parallel universes. By suggesting the existence of extra dimensions and the potential for multiple configurations of spacetime, string theory offers a way to connect different universes within the multiverse. While the concept of parallel universes connected by string theory is still speculative, it opens up exciting possibilities for understanding the deeper structure of reality. Whether or not string theory ultimately proves to be the correct framework for the multiverse, it provides a powerful and elegant way of thinking about the nature of the universe. and the possibility that we are part of something far larger and more complex than we can currently comprehend. As our understanding of string theory and the multiverse evolves, we may one day uncover new insights that will change our view of the universe and our place within it. For now, the multiverse remains one of the most exciting and provocative ideas in modern physics, pushing the boundaries of what we know and opening up new possibilities for exploration and discovery. As we venture deeper into the mysteries of the universe and parallel universes, we encounter one of the most provocative ideas of the 21st century, the simulation hypothesis. This theory proposes that our entire reality, from the laws of physics to the stars in the sky, could be a highly sophisticated computer simulation created by an advanced civilization. The idea that we might be living in a simulated reality has far-reaching implications for our understanding of the universe, consciousness, and existence itself. Could parallel universes, the multiverse, and the very fabric of space-time be the product of a simulation? And if so, how does that affect our place in the cosmos? In this chapter, we will explore the simulation hypothesis, its philosophical roots, and its connection to the idea of parallel universes. We will look at the leading arguments for and against the hypothesis, examine the possibility of digital consciousness, and explore the fundamental questions it raises about the nature of reality. Is our universe the only one that exists, or could we be living in a simulated version of reality within a larger multiverse of simulations? The simulation hypothesis. A brief overview. The simulation hypothesis suggests that everything we perceive, every atom, every galaxy, every thought, might be the product of a computer program. In this view, what we experience as the real world is actually a simulation running on a super-intelligent computer created by a highly advanced civilization. This idea has gained considerable traction in recent years, especially with the rise of digital technology, artificial intelligence, and virtual reality. The concept of a simulated reality is not entirely new. Philosophers have speculated about the nature of reality for centuries, with ideas ranging from Descartes' evil demon hypothesis, which posited that a malevolent force could be deceiving us into believing in a false reality, to Plato's allegory of the cave, in which prisoners perceive only shadows on a wall, mistaking them for reality. However, it was the advent of modern computing, combined with developments in theoretical physics, that brought the simulation hypothesis into the realm of serious scientific and philosophical discussion. One of the most well-known proponents of the simulation hypothesis is Nick Bostrom, a philosopher at the University of Oxford. In his 2003 paper, Are You Living in a Computer Simulation?, Bostrom argued that one of three possibilities must be true. 1. Human civilization is unlikely to reach a level of technological development capable of creating realistic simulations of entire universes. 2. If advanced civilizations can create simulations, they are unlikely to do so, either because they do not wish to or because they consider it unethical. 3. We are almost certainly living in a computer simulation. Bostrom's argument is based on the assumption that as civilizations become technologically advanced, they will gain the ability to simulate entire universes. If this is the case, then the number of simulations created could far exceed the number of real universes. As a result, the probability of living in a simulation increases dramatically. This argument does not necessarily claim that we are living in a simulation, but it makes the case that the possibility is far from implausible. If we follow Bostrom's reasoning, the question is not whether it's possible to live in a simulation, but how likely it is given the technological trajectory of future civilizations. The technological foundations of the simulation hypothesis. For the simulation hypothesis to hold any merit, it requires a high level of technological development, a civilization capable of simulating an entire universe, including the complexities of space, time, and even consciousness. To put it in perspective, a civilization would need computational resources many orders of magnitude greater than anything humanity currently possesses. In order to create a simulation of an entire universe, advanced civilizations would need to simulate not just the particles and forces that govern physical reality, but also the laws of physics, chemistry, and biology that allow complex structures, such as life, to emerge. The level of detail required for such a simulation would be staggering, as the simulation would need to account for the interactions of every subatomic particle, the dynamics of entire galaxies, and the experiences of conscious beings. Today, our most advanced simulations are limited to relatively simple systems, such as weather patterns, molecular dynamics, or video game worlds. While these simulations are impressive, they are far from replicating the complexity of the universe. However, as technology continues to progress, we may reach a point where simulations are sophisticated enough to replicate entire universes. The development of quantum computing, computers that use quantum bits, qubits, rather than classical bits to process information, is one area where we might see significant advances. Quantum computers have the potential to solve complex problems far faster than classical computers and may one day provide the computational power required to run universe-scale simulations. As AI continues to improve, we may also develop the algorithms necessary to create truly intelligent simulations capable of emulating the behavior of living organisms and conscious beings. In short, the simulation hypothesis assumes that civilizations can advance to a point where they possess the computational power to simulate entire universes. While this is still speculative, it is not outside the realm of possibility given the rapid pace of technological progress. Digital consciousness, could we be programs? One of the most profound implications of the simulation hypothesis is the idea of digital consciousness. If our universe is a simulation, then the consciousness we experience, our thoughts, emotions, and perceptions, could be nothing more than the result of a sophisticated program running within the simulation. This raises the question, what does it mean to be conscious? If our minds are simply programs running on a supercomputer, are we truly alive, or are we merely simulations of conscious beings? Could our experience of self-awareness and the feeling of I be nothing more than a digital illusion? The idea of digital consciousness challenges our traditional understanding of consciousness as something tied to the biological brain. In the simulation hypothesis, consciousness could arise from complex algorithms, much like how characters in a video game experience a form of artificial consciousness within the game world. If this is true, then consciousness is not necessarily tied to biological processes, but could exist as the result of complex information processing in a virtual environment. Philosophers have long debated the nature of consciousness. The hard problem of consciousness, as described by philosopher David Chalmers, asks why and how subjective experiences arise from physical processes in the brain. If consciousness can be replicated in a simulation, it might suggest that the subjective experience of awareness is not limited to biological organisms, but could emerge from any sufficiently advanced system capable of processing information. The potential for simulations. Within simulations. One of the most unsettling aspects of the simulation hypothesis is the possibility of nested simulations, simulations within simulations. If we are living in a simulation, then it's conceivable that the creators of the simulation could have created their own simulations, and those simulations might themselves contain other simulations. In this scenario, we could be part of a chain of simulations, each running within a more advanced simulation. This idea leads to a recursion problem, where we might never be able to prove or disprove whether we are living in the base reality or simply in a simulation. Every level of simulation would appear real to its inhabitants, and there might be no way to detect whether the world they live in is the original universe or one of many simulated realities. Furthermore, the idea of nested simulations raises questions about free will and determinism. If we live in a simulation within a simulation, and each level of reality is controlled by the creators of the simulation, then our thoughts and actions might not be our own. Instead, they could be the result of predetermined algorithms running in a supercomputer. The implications for free will are profound, as it would suggest that our sense of autonomy could be an illusion created by the simulation itself. Evidence for the simulation hypothesis. While the simulation hypothesis is provocative, it is currently a speculative theory with little empirical evidence to support it. Some proponents of the hypothesis, such as Elon Musk, have argued that the rapid advancement of virtual reality and gaming technologies could soon provide us with the capability to create realistic simulations. According to Musk, the fact that we already live in an age of virtual reality games and artificial intelligence suggests that creating a simulation as sophisticated as the one we experience is merely a matter of time. Some physicists have suggested that there could be signs of a simulation embedded within the laws of physics. For example, the pixelated nature of space-time, the idea that space-time is not continuous but made up of discrete units, could be a sign that our universe is a simulation. This idea comes from the study of quantum mechanics, where certain phenomena suggest that the universe might have a finite resolution, similar to how a digital image is made up of pixels. If space-time were discrete at the smallest scales, this could indicate that the universe is being simulated on a digital platform. Another potential piece of evidence for the simulation hypothesis comes from the fine-tuning of the universe. The constants of nature, such as the strength of gravity and the electromagnetic force, seem to be perfectly calibrated to allow for the existence of life. Some have suggested that this fine-tuning could be the result of the simulation's parameters being set to ensure life could emerge, much like a video game's designers adjusting the settings to make the game world more habitable for its characters. Philosophical and existential implications. The simulation hypothesis raises profound philosophical and existential questions. If we are living in a simulation, does that mean that our reality is somehow less real than the base reality? Are our lives, relationships, and experiences meaningless because they are part of a computer program? What happens when we realize that the world around us is a simulation? Does it change how we experience life? The idea that our universe might be a simulation also touches on the nature of reality and the meaning of existence. If we are mere programs in a simulation, does that invalidate our subjective experiences? Can we still find meaning, purpose, and fulfillment in a world that might be artificial? These questions are deeply philosophical and challenge the fundamental assumptions we have about consciousness, free will, and the meaning of life. In many ways, the simulation hypothesis forces us to confront ontological questions about what it means to exist. If we are conscious beings living in a simulation, are we any less real than the creators of the simulation? Does the artificial nature of our world diminish our experiences, or does our subjective perception of reality validate its authenticity? Conclusion. The simulation hypothesis. A new perspective on reality. The simulation hypothesis offers a radically different view of reality, one that suggests that everything we experience, from the stars in the sky to the emotions we feel, might be the product of a highly advanced computer program. Whether we are living in a simulation or not, the idea challenges our understanding of consciousness, reality, and existence itself. While the simulation hypothesis remains speculative and lacks definitive proof, it raises important questions about the nature of reality and the future of science and technology. As our capabilities in virtual reality, artificial intelligence, and quantum computing continue to advance, we may one day reach a point where we can create simulations that are indistinguishable from the real world. If that happens, the line between real and simulated will become even blurrier, forcing us to reconsider our assumptions about the universe. The simulation hypothesis also invites us to explore the deeper mysteries of existence, free will, and the meaning of life. Whether we live in a simulation or not, the search for answers to these questions will continue to inspire our quest for knowledge and understanding of both the universe we live in and the nature of reality itself. The idea of parallel universes, separate independent realities existing alongside our own, is a mind-bending concept. But what if these parallel universes could be accessed? What if time travel were not just a hypothetical concept, but a possible gateway to other realities? Could we, through manipulation of time, move between different universes, exploring alternate histories and divergent realities? In this chapter, we will explore the connection between time and parallel universes. We will investigate whether time travel could serve as a method for traveling between parallel realities and whether the mechanics of time itself allow for movement across different versions of reality. We will also discuss the theories of time travel, including those proposed by Einstein's relativity and quantum mechanics, and how these theories could potentially lead to the discovery of parallel universes. What is time? Before diving into the possibility of time travel to parallel universes, it is essential to first understand what time is. Time is one of the most fundamental aspects of our experience of reality. It is a continuous progression from the past through the present and into the future. However, despite being a fundamental feature of our everyday lives, time remains one of the most elusive and mysterious concepts in science and philosophy. In classical physics, time was considered an absolute flowing uniformly for all observers, independent of the events happening around it. However, Albert Einstein's theory of relativity fundamentally altered our understanding of time. In Einstein's view, time is not a constant fixed entity. Instead, time is relative and can be influenced by factors such as velocity and gravity. This led to the realization that time is part of a four-dimensional continuum known as space-time, where time is intertwined with the three dimensions of space. In Einstein's special relativity, time appears to move differently for objects in motion compared to those at rest. The faster an object moves, the slower time flows for it, a phenomenon known as time dilation. For instance, an astronaut traveling at close to the speed of light would experience time much more slowly than someone on Earth, resulting in time travel to the future. In general relativity, time is further affected by gravity. Near massive objects like black holes, the fabric of space-time is warped, causing time to pass more slowly compared to regions of space with weaker gravitational fields. This effect, known as gravitational time dilation, suggests that time itself is not only relative to velocity, but also to the presence of massive objects in space. Understanding the relativity of time is essential when considering the possibility of time travel. If time is flexible and can be altered by velocity or gravity, could there be a way to manipulate time in such a way that we could travel through it and potentially to other parallel universes? Theories of time travel and parallel universes. Now that we have a basic understanding of time, let's explore whether time travel could allow us to access parallel universes. If time can be manipulated, could there be a way to travel not just within our own universe, but between multiple realities? Time travel to the future. One of the most well-known predictions of Einstein's theory of relativity is that time travel to the future is not only theoretically possible, but also scientifically supported. According to special relativity, when an object moves at speeds close to the speed of light, time slows down for that object relative to an observer at rest. This means that astronauts traveling at relativistic speeds would experience time at a slower rate than people on Earth. While the astronauts might only age a few years, many years would pass on Earth. This is a form of time travel to the future. In fact, experiments with particles traveling at relativistic speeds have demonstrated this time dilation effect. Atomic clocks flown on airplanes have shown that time passes slightly more slowly for objects in motion compared to those at rest. While this effect is negligible at everyday speeds, at velocities close to the speed of light, the effect becomes profound. Therefore, in theory, if we could build spacecraft capable of approaching the speed of light, we could travel into the future. The question then arises, could time travel to the future lead to the discovery of parallel universes? The answer is unclear, but it depends on the nature of time and the potential for multiple timelines. Time travel to the past and parallel universes. While time travel to the future is theoretically feasible, time travel to the past presents more significant challenges, including the potential creation of causal paradoxes. The most famous of these is the grandfather paradox, which poses the question, what happens if you travel back in time and prevent your grandfather from meeting your grandmother? If your grandfather never meets your grandmother, you would never be born. So how could you go back in time to prevent their meeting in the first place? To resolve these paradoxes, some physicists propose that time travel to the past might not alter the course of history in a single timeline, but could instead result in the creation of an alternate timeline or parallel universe. This idea is supported by the many worlds interpretation of quantum mechanics, which suggests that every time a quantum event with multiple outcomes occurs, the universe splits into separate branches, each representing a different outcome. In the context of time travel, this interpretation implies that if you were to travel back in time and alter the past, you would not change your own universe, but instead create a new parallel universe in which history unfolds differently. This model suggests that the timeline you return to would not be the one you originally came from, but a new reality that exists alongside your original universe. In this framework, time travel becomes a gateway not just to the past, but to parallel universes, with each act of time travel potentially creating a new branch of reality. This could mean that each time a time traveler interacts with the past or future, they are effectively creating a new version of history, a new universe that exists parallel to their own. Wormholes and time. Travel to parallel universes. Another intriguing possibility for time travel comes from the theoretical concept of wormholes, tunnels through spacetime that could, in theory, allow for faster-than-light travel or instantaneous travel between distant points in space. If wormholes exist, they could offer a means of traveling between different parallel universes by providing a shortcut through space-time. Wormholes are solutions to the equations of general relativity that describe the warping of space-time. In simple terms, a wormhole connects two separate points in space-time, allowing an object to travel between them without traversing the intervening space. If wormholes exist, they could theoretically allow for travel to other points in time, or even to entirely different universes. Some physicists speculate that if wormholes could be stabilized and made traversable, they could connect not only different points in space, but also different versions of reality. A wormhole could connect parallel universes, providing a physical bridge between them. In this scenario, time travel would not only allow us to visit the past or the future, but also to explore alternate realities. The challenge, however, is that wormholes, if they exist, would be incredibly unstable and would require the presence of exotic matter with negative energy to keep them open. Additionally, wormholes would likely be located in extreme environments, such as near black holes or in other high-energy regions of space, making them difficult to study or use for practical purposes. Despite these challenges, the idea of wormholes as a potential means of accessing parallel universes remains one of the most exciting possibilities in theoretical physics. The role of quantum mechanics in time travel to parallel universes. At the subatomic level, quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales, plays a crucial role in our understanding of time and parallel universes. Quantum mechanics introduces the idea of superposition, where particles can exist in multiple states simultaneously. This leads to the possibility that the universe itself could exist in a superposition of states, with each possible outcome occurring in a separate parallel universe. The many worlds interpretation of quantum mechanics suggests that every quantum event with multiple possible outcomes results in the splitting of the universe into multiple branches. In this framework, time travel would not just create one alternate timeline, but an infinite number of universes, each with a different version of history. This means that every time a decision is made or an event occurs with multiple possible outcomes, a new universe is created, corresponding to one of the possible outcomes. In terms of time travel, this interpretation suggests that when a time traveler goes back in time and alters the past, they are not changing their original timeline, but rather creating a new one. This branching of the universe could lead to the creation of an infinite number of parallel universes, each corresponding to a different version of reality. Time travel, therefore, becomes a means of exploring the multiverse, with each journey creating new timelines and new universes to discover. Challenges of time travel to parallel universes. While the idea of time travel to parallel universes is an exciting and tantalizing possibility, there are many challenges and unknowns associated with it. Theoretical models of time travel, such as those based on wormholes or quantum mechanics, often rely on exotic concepts like negative energy and exotic matter, both of which remain speculative and unproven. Additionally, the potential for causal paradoxes and the creation of multiple timelines presents significant logical and philosophical challenges. Moreover, the energy required to manipulate space-time on such a grand scale, to create or stabilize a wormhole, for example, is beyond anything we can currently conceive. Current technology is nowhere near capable of achieving the necessary energy levels, and the practical difficulties of time travel remain overwhelming. Furthermore, if time travel does create parallel universes, the question arises of whether these universes are truly accessible. If each new timeline is completely separate from the others, how would a time traveler know which universe they are in? Would they be able to return to their original reality, or would they be lost in a new version of history forever? Conclusion: time travel as a gateway to parallel universes. Time travel to parallel universes remains one of the most speculative and mysterious ideas in theoretical physics. While the theories surrounding time travel, including those based on relativity, quantum mechanics, and wormholes, offer tantalizing possibilities, we are still far from understanding how such travel might be achieved, let alone whether it is even possible. If time travel to parallel universes were possible, it could open up an entirely new realm of exploration, where entire new histories and alternate realities could be visited. However, the challenges of time travel, both theoretical and practical, are immense. Even if time travel were achieved, it might not be a simple matter of visiting alternate realities. The consequences of altering time or traveling to parallel universes could be profound and unpredictable. For now, the possibility of time travel remains a fascinating area of scientific research and philosophical inquiry. Whether or not we will one day be able to travel through time and access parallel universes, the pursuit of this idea continues to push the boundaries of what we know about the nature of reality, time, and existence itself. The concept of parallel universes has captivated the human imagination for centuries, inspiring countless works of science fiction and spurring debates in the fields of philosophy, physics, and cosmology. But despite its long-standing popularity in popular culture, the question remains, will we ever prove that parallel universes exist? As we've explored in previous chapters, the idea of parallel universes, or multiverses, is not just a theoretical concept, but one that is deeply rooted in the foundations of modern physics. From quantum mechanics to string theory and cosmology, the scientific community has developed several compelling theories that suggest the existence of parallel realities. But even with these theories in hand, the challenge of finding definitive proof of parallel universes remains immense. In this chapter, we will explore the future of parallel universe research, examining the scientific advancements that could bring us closer to proving their existence. We'll discuss the tools and technologies that might allow us to detect parallel universes, the theoretical obstacles that stand in our way, and the potential breakthroughs that could transform our understanding of reality. Ultimately, we will ask the question, is the existence of parallel universes something we will ever be able to prove, or are we destined to remain in the dark about the true nature of reality? The search for evidence of parallel universes. The search for evidence of parallel universes is one of the most exciting and challenging areas of modern physics. If parallel universes exist, they may be fundamentally different from our own, governed by different physical laws, constants, and histories. These alternate universes might be completely disconnected from ours, making it difficult, if not impossible, to detect them using traditional methods. However, there are several theoretical and observational approaches that physicists believe might one day provide evidence for the existence of parallel universes. 1. Cosmic microwave background radiation. One of the most promising sources of evidence for parallel universes comes from the study of the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. The CMB is the oldest light in the universe, dating back to just 380,000 years after the Big Bang. It provides a snapshot of the early universe, revealing the conditions that existed just after the formation of the first atoms. Some researchers have suggested that the CMB may contain subtle signatures of parallel universes. In particular, certain anomalies in the CMB, such as patterns or irregularities in the distribution of temperature, could indicate the presence of other universes. If our universe is part of a multiverse, it is possible that the gravitational influence of other universes could leave imprints in the CMB, similar to how the gravity of nearby objects can distort the fabric of space-time. While no definitive evidence has yet been found, researchers are continuing to analyze the CMB for any unusual patterns that could suggest the existence of parallel universes. In the future, more advanced instruments and data analysis techniques could help uncover hidden clues about the structure of the multiverse. 2. Gravitational waves. Another potential avenue for detecting parallel universes is the study of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. Gravitational waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, and since then they have provided a new way of observing the universe. Some theories of the multiverse suggest that the collision or interaction of different universes could produce detectable gravitational waves. If parallel universes exist and influence each other, their interactions might generate gravitational waves that could be detected by sensitive instruments like LIGO or the Virgo detector. These waves could serve as indirect evidence of the existence of other universes and provide valuable insight into the nature of the multiverse. While the idea of detecting gravitational waves from parallel universes is speculative, it is a promising area of research that could provide a new way of probing the very fabric of space-time. 3. Theoretical models of quantum mechanics. One of the most significant theoretical approaches to understanding parallel universes comes from quantum mechanics, particularly the many-worlds interpretation, MWI. The many-worlds interpretation suggests that every quantum event with multiple possible outcomes results in the splitting of the universe into different branches, with each branch representing a different outcome. According to this interpretation, every decision or event that can occur in multiple ways results in the creation of a new parallel universe. In theory, the universe is constantly splitting into new branches, each corresponding to a different version of reality. While this idea is compelling, it has not yet been proven. The challenge lies in the fact that each of these parallel universes is completely disconnected from our own, meaning there would be no direct way to interact with or observe them. However, some physicists believe that the many-worlds interpretation could be tested indirectly through experiments involving quantum entanglement and quantum superposition. If the many-worlds hypothesis is correct, it may be possible to detect the subtle effects of parallel universes on quantum systems, potentially providing evidence for the existence of multiple realities. 4. The string theory landscape. String theory, which proposes that the fundamental building blocks of the universe are tiny vibrating strings, offers a potential framework for understanding the multiverse. According to string theory, there could be an infinite number of possible universes, each with its own set of physical laws and constants. These universes would exist in a higher dimensional space, and the extra dimensions predicted by string theory could provide a way for these universes to be linked. The idea of a landscape multiverse suggests that there are an enormous number of possible configurations of the extra dimensions in string theory, leading to a vast number of different universes. The landscape is often referred to as the collection of all possible solutions to the equations of string theory, each corresponding to a different universe. If this model is correct, then there could be an infinite number of universes, each with its own unique properties. One challenge of string theory is that it is difficult to test. The extra dimensions predicted by string theory are thought to be incredibly small, far smaller than anything we can currently observe with existing technology. However, Future advancements in particle accelerators, such as the Large Hadron Collider, LHC, could potentially provide insights into the nature of these extra dimensions and whether they are connected to parallel universes. Philosophical and conceptual challenges of proving parallel universes. While there is a growing body of theoretical and observational work supporting the idea of parallel universes, there are significant philosophical and conceptual challenges in proving their existence. One of the biggest challenges is that parallel universes, by their nature, are fundamentally unobservable. If each universe in the multiverse is completely isolated, there may be no way to directly interact with or detect these alternate realities. This raises important questions about the nature of scientific proof and whether the concept of parallel universes is even testable. Can a scientific theory be considered valid if it cannot be experimentally verified? Should the multiverse hypothesis be dismissed because it is fundamentally untestable, or should it be considered a valid scientific theory based on its mathematical consistency and its potential explanatory power? Additionally, if parallel universes exist, do they adhere to the same laws of causality that govern our universe? In many multiverse models, the idea of inter-universe causality is murky at best, and interactions between universes, if they are even possible, remain speculative. This creates another philosophical dilemma. If parallel universes can influence one another, how would we reconcile their interactions with the fundamental laws of physics? Technological limitations and future prospects. The search for evidence of parallel universes faces significant technological limitations. As mentioned earlier, much of the evidence for parallel universes depends on the detection of subtle anomalies in cosmic radiation, gravitational waves, or quantum systems, all of which require advanced detection instruments. However, our current technologies are far from capable of directly observing parallel universes. Instruments like LIGO, Planck, and the Hubble Space Telescope provide valuable data about the universe, but they cannot detect the existence of other universes or observe events in parallel realities. As technology improves, there may be new ways to test the existence of parallel universes. Quantum computers, which are still in the early stages of development, could provide new insights into quantum mechanics and the many worlds interpretation. Future space missions and more powerful telescopes might allow us to explore deeper into the cosmos and potentially detect anomalies or imprints from other universes. The development of new theories in cosmology, quantum mechanics, and string theory might offer the tools we need to test the multiverse hypothesis more rigorously. While the search for parallel universes remains speculative, the questions it raises continue to push the boundaries of human knowledge. Even if we never find definitive proof of parallel universes, the exploration of this concept will continue to inspire new ideas and innovations in physics, cosmology, and philosophy. Conclusion: will we ever prove parallel universes exist? The search for parallel universes is one of the most exciting and challenging endeavors in modern science. While there is growing theoretical and observational evidence to suggest that multiple universes may exist, the task of proving their existence remains daunting. Theoretical models such as quantum mechanics, string theory, and inflationary cosmology all provide frameworks for understanding the multiverse, but the direct detection of parallel universes is an obstacle that we have not yet overcome. As technology advances and our understanding of the universe deepens, we may one day find the tools needed to test the existence of parallel universes. However, the very nature of these universes, potentially separated from ours by higher dimensional space or completely unobservable, poses significant challenges to experimental verification. The pursuit of evidence for parallel universes, however, continues to push the boundaries of our knowledge, forcing us to rethink our understanding of reality itself. Whether or not we ever prove the existence of parallel universes, the journey to explore these possibilities will inspire new discoveries and deepen our understanding of the cosmos, our place within it, and the nature of existence itself.